Well, thank you, Jerry, for this introduction. The results I want to present are part of the PhD works of Markus Kohn and Thomas Rohm. They decided not to come to Catania, so I have the luck to present you their results again. We heard a lot about the very high cycle fatigue loadings and the impact on the technical applications, so I have not to tell you much more. And then there are a lot of components influenced in this lifetime ratio, and therefore it's necessary to have a high reliability to use this kind of materials which are sensitive to high cycle fatigue failure, to very high cycle fatigue failure, and to understand what is the reason why the same material in different heat treatment conditions is sensitive to high cycle fatigue or non-sensitive to very high cycle fatigue failure. Right? So everybody knows that in some material states we have a second drop of the resistance against fatigue in the number of cycles higher than 10 to the 7. So what we do is we try to understand for common material in different heat treatment states what are the reasons for failure in the very high cycle fatigue ratio. So we tried to evaluate the damage mechanisms and to understand what is the reason for the failure, and this would be the basis to make a lifetime prediction which is oriented on the mechanisms which are acting. So this is my outline. I want to tell you something about the material and the state of the material we investigated, and give you some information about our special setup, experimental setup we used, and then present experimental results and make some assessment on the fatigue strength and of the lifetime, summarize and tell you what we are planning in the near future in the outlook. So the material we investigate is a typical quenched and tempered material. It's a 42crmo4, and we first investigate the material. So the cleanliness is very important. How many non-metallic inclusions are, and we found that the non-metallic inclusions could be summarized with a Gumbel extreme value distribution. They are mainly oxides, aluminium, calcium oxides, which are contained in the material. So we made different heat treatments to influence the strength of the material. First, it was austenite at 850 degrees centigrade for 20 minutes and then quenched to room temperature in oil. And after that, it was tempered at different temperatures, which are given here, to influence the ultimate strength and also the deformation behavior. So this different tempering temperature results in ultimate strength between 1050 megapascals and 2200 megapascals, and the ultimate strain ranges between 30% and 5%. So because we made these heat treatments at the specimens which were close to the final shape, we have some influences of residual stresses coming from the heat treatment. So the specimens treated at high temperature have low compressive stresses, very low compressive stresses. The one which was heat treated at 500 degrees centigrade has nearly no residual stresses at the surface, but the specimen tempered at lower temperature has some tensile residual stresses, but only at the surface, and it's not reaching very deep. Also, the content of retained arsenic is very low, is below 3.5 volume percent, and you can see this retained autunite in micrographs. So the experimental setup, we performed two types of tests. The first one is conventional fatigue test using a conventional servohydraulic system at 50 Hertz. The second type, we use a self-developed resonant fatigue machine, a testing facility which is built up by our own. We have a voice coil actuator which acts on a flywheel mass which is fitted to the stiffness of the specimen and to the loading track. So the mass is adjusted to get a test frequency in the range of 1 kHz. 1 kHz is, it is possible to make force measurement by coupling the specimen directly to a load cell, so we did not have to calculate our loading from the displacement of the specimen head. It is necessary at the ultrasonic testing system. This is the type of machine we have no mean load, it's just equal -1, and we tried to perform our tests at room temperature. It's not so easy because, especially in the low strength states, there is a self-heating of the specimen, and therefore we added some nozzles to blow compressed air to the specimens, or the surface of the specimens. So we tried to keep the surface temperature below a temperature increase of 10 degrees. Let's say normally in our lab we have 20 degrees centigrade. So the temperature of the specimen remains below 30 degrees centigrade. We can measure the force amplitude and can also evaluate the frequency domain of our loading, and we can also monitor the testing frequency which is close to the resonant frequency of the loading track. The specimen we investigated here is shown. It's a full round specimen, solid round specimens with a diameter of 5 millimeters within the ghost length, and the ghost length has 5 millimeter length. So the highly stressed volume ranges up to 63 millimeters. Cubic millimeters. So let me come to the experimental results. Here are the two orders of our strengths which we investigated. The left one is for the annealing temperature, the temporary temperature of 550 degrees centigrade, and the other one is for a temporary temperature of 90 degrees centigrade. As you can see, there is the typical Wöhler behavior for the low strength or the medium strength state, where we have only failure below number of cycles to failure of 10 to the 7. There is no failure in the very high cycle fatigue ratio. These are every point here is a run out. And you can also see a small difference between 50 Hertz and 1 kilohertz results. At 50 Hertz we have an ultimate fatigue strength of about 460 megapascal, and at 1 kilohertz the staircase method results in a fatigue limit of roughly 410 megapascal. So the higher frequency reduces the fatigue strength about 10%. In the low tempered state, in the high strength state, we see a clear influence of the very high cycle fatigue failure. These are all failures. So we have two different slopes of Pascal equations, one steeper slope in the high cycle and low cycle fatigue range, and a flatter slope in the very high cycle fatigue range. And again, there is a small difference of about 10% between 1 kilohertz and 50 hertz testing frequency, and we think this is attributed to a self-heating part of the failure. So when we look on the crack initiation type, when we have a very high loading, there is a multiple crack initiation. When we go to higher numbers of cycle to failure or lower loadings, there's only one ignition site for failure, but when we stay in the high cycle fatigue range, there is just the surface important in both cases, in the high and in the medium state of the material. In the very high cycle fatigue strengths, it turns to inclusion-induced damage, again, as we all know, and we can separate in two types of inner inclusion. For the higher loading and the lower lifetimes, there we get no optical dark area around the inclusions, and only for the very high cycle fatigue range at the higher numbers there is a formation of an optical dark area by inclusion. So when we evaluate the fatigue strengths, we can change in different ultimate numbers of cycles to define the fatigue strengths. Here we will regard on 10 to the 6 as one ultimate number of cycles and 10 to the 9 as the other one. When we take 10 to the 6, we get the typical behavior as we expected, with increasing strengths, ultimate strengths of the material. We get first an increase of the fatigue limit, which is plotted on the other axis, and for the very high strength materials there will be a decrease. We are still with our material in a flatter curve of this. And you can also see the difference between 50 Hz, which is the black line, and 1 kHz, which is the blue line. And again, 90% of the material, 90% of the reduction of 10% will occur of the fatigue strength. But when we chose 10 to the 9 as fatigue limit, we get no influence up to an ultimate strength of about 1400 megapascals. But for higher strength materials, we get a reduction of the fatigue strength, which could be described by such a factor, and we observed a nearly linear behavior, nearly a linear reduction depending on the fatigue strengths which we observed at the 10 to the 6. So there is some sensitivity to very high cycle fatigue failure for materials, for our materials with a higher fatigue strength than 1400 degrees centigrade, and no influence for lower strengths. So I see I run out a bit of time, so there is a typical evaluation using the fracture mechanics according to Murakami, and we can see that when we are looking on the stress intensity which is induced by the oxides, there is a clear dependence. There is no statistical improvement, but there are trend lines which coming from the description for the different tempering temperatures. When we add the optical dark area to the inclusion size, and we calculate the stress intensity factor, the maximum stress intensity factor, there is also no clear influence of our temperature, of the tempering temperature. So when we can use these calculations to assess the lifetime, at first the fatigue strength, and there is a complex influence of the size of the inclusions. XZ means it's the addition of the inclusion size plus the optical dark area if it occurs. And also on the position of these inclusions, on the ultimate strengths, and on the applied mechanical strain. More details will be given in the proceedings, which are just read accepted. So you can see. The more important thing for us is to describe the lifetime behavior using a Pascal equation. And according to an approach of Akewina, you can interpret the slope of the Pascal equation as the reverse of the fatigue crack growth rate. And when we apply this approach, we can determine that in the crack growth rate vary between 10 to the minus 20 and 10 to the minus 5, depending on the hardness of the material. From our point of view, this makes no really physical sense, because this means that the crack growth rate is less than the Leddy constant, so it must be discontinuous crack growth, or there must be another effect to which goes with it. But we can use this explanation to describe the lifetime behavior, and this is none other than the slope of the Pascal approach. Just brought it to the straight to the size of the inclusions. And so the occurrence may be enough for technical applications. So my summary: we investigated the material, is a neat material at different strength states, and we found that the decreasing Kmax is the Kmax, which are induced by inclusion in the optical dark area, increased with the number of cycles to failure. Then it could be described in a very high cycle regime by a modified Pascal, which is connected to the parameters of the Pascal law in this. So what we now need is to describe the lifetime basing on the mechanism which acted, and therefore we need a model to describe the nucleation of this optical dark area. Therefore, at the moment, there is no really physical-based model, so we have to think about how can we describe this. The rest, if this optical dark area is formed, it could be described by the normal Paris law, and we only have to evaluate the Paris law parameters for the different medium. So what we need is, how can we describe the formation of the optical dark area? So thank you very much.